Okay, so here we are looking at once again operating systems. All right. And we were talking about threading yesterday, right? But there are a few issues that come up with threading. And, you know, one thing that this makes me think about are some of the issues that came up with multiprocessing in general. You may have heard of lightweight threads. Some people have, some people have not. And there was something called fibers in lightweight threading, which is kind of like, how lightweight or how threads are lightweight processes. There's something called fibers, which is supposed to be lightweight threads, and they've been pretty hard to manage, right? So you'll see that there are various implementations in different areas. I believe Ruby programming had fibers at one point, and Windows operating system also had fibers, which were lightweight threads. And then later on, you had implementations of what they call coroutines, right? So I believe Go and Rust use coroutines, and there are other APIs that use coroutines as opposed to fibers to handle similar issues in which you have, lightweight threading type of tasks, right? So now here we're talking about threading issues to consider about multi-threaded programming. Let's take a look. So before we talked about system calls, right? Fork and exec. Now, exec allows you to run other processes or programs from the kernel level. All right. So that's what exec does. Now, if one thread in a program calls fork, does the new process duplicate all threads, or is the new process single threaded? Some Unix systems have chosen to have two versions of fork, one that duplicates all threads and another that duplicates only the thread that invoked the fork system call. The exec system call typically works in the same way as described in chapter 3, which is to say that if a thread invokes exec, right, the program specified in the parameter to exec will replace the entire process, including all threads. All right. So you might say that that process, not just the thread that called exec, but the process and all of the other threads would die off in favor of exec actually running. Yikes. So now, in the case of fork, which implementation is used depends on the application. In the case of exec, if exec is called immediately after forking, then duplicating all threads is unnecessary. Okay. And that would be for obvious reasons. You see, if we call fork, we're going to create a new process. If that new process creates, or if that new process decides to call exec, it's going to call it in the context of a new process, not in the former process with the previous thread pool. Okay. Uh, so now, in that case, if exec is called immediately after forking, then duplicating all threads wouldn't be necessary as the program specified in the parameters to exec will replace the process. In this instance, duplicating only the calling threads would be appropriate. Okay, so only duplicating the calling threads is what we would do. Now, going one step farther, if the separate process doesn't call exec after forking, the separate process should duplicate all threads. I'll repeat that again. If the separate process doesn't call exec after forking, the separate process should duplicate all threads. All right, so here we're talking about what happens when we have a process. If it's just like a child process of the previous thread for the previous process, then there's a duplication of the threads so that it's basically going to be similar to the parent process. However, if we actually change uh, the runtime by calling exec and running a separate program or a different process altogether, right? In that case, you simply would have exec not duplicate everything, but just take over the whole that particular continuity of the runtime, right? And then rather than creating more threads, it would just basically work as exec was supposed to work. But in this case, it's running instead of the process or the thread that called it or invoked it, right? So that's what they're saying about there being two versions of fork, right? So imagine we call fork, then after that we call exec. We don't duplicate all the threads. Instead, the program specified would then replace the process. Okay, so that's what happens. The fork would basically be a fork that will lead to, that exec program. And in the case of, if we don't call exec, then we would have that whole replication. So now thread cancellation is the task of terminating a thread before it has completed. Now, remember what I showed you before with things like MPI and Java and the P threads, right? So imagine that we have multiple threads trying to work all together to finish some sort of task, a distributed task. And then before they can all return, we decide that we're going to terminate a thread, right? So if whatever has been finished gets terminated at a certain point in time, all right? So instead of, getting the remainder of our results, we immediately stop and return. And whatever happened, happened. Whatever did not, did not. The remaining threads might be canceled if only we should call a termination procedure before, all of the threads have returned. Once they have returned, that would be one thing. We may retain, any sort of um, result from that execution. But as for the ones that did not, we basically are stopping them from any further execution, and that's just that. So a thread that is going to be canceled is often referred to as the target thread. And then when we cancel the target thread, this occurs in the following scenarios. There could be a deferred cancellation, right? The target thread periodically checks whether it should terminate, allowing it an opportunity to terminate itself in an orderly fashion, kind of like a clean shutdown, right? And in this particular case, if the resource is allocated to a canceled thread, or a thread is canceled while in the midst of updating data it's sharing with other threads, then you're going to have some complications, right? And in the case that we're having something like, say, asynchronous cancellation, where some threads are canceled, others may be farther along in their execution, the operating system will then reclaim system resources from canceled threads, but will not reclaim them all, right? So in this particular case, a canceled thread or canceling threads asynchronously, they may not free necessary system-wide resources. And that would be bad for, um, some sort of task that was supposed to be running, but it's not running, and the resources are still not available for threads that are running. We wouldn't want that to happen. So in this particular case, with the deferred cancellation, you would have one thread that indicates that a target thread is to be canceled, but cancellation occurs only after the target thread has checked the flag to determine whether or not it should be canceled. And the thread can perform this check at a point at which it can be canceled safely. And P threads refers to such points as cancellation points. So now, signals in Unix and signal handling. You use signals in Unix to notify processes that particular events have unfolded. and a signal can be received either synchronously or asynchronously. So it can either be done at a point in time that is expected or just at any given point in time because it does not depend on the execution of some parallel running process or thread. So then in this case, all of these different signals, despite how they run, they're going to have the following characteristics. Number one is that the signals generated by the occurrence of a given event. And a generated signal is delivered to a process. And once delivered, the signal must be handled. So this is what we were referring to or talking about at one point when we spoke about signals coming up in interrupts, right? Here you see a signal is generated, is sent to the process, and it is not just delivered um, after some event occurs, but it has to be handled um, once it is received, right? So now things that can happen that would cause signal to come up could be things like illegal memory access or arithmetic errors. Um, Also, in certain cases, and hopefully, we don't have these things too often because many programming environments actually check for these things. But these signals are delivered to the same process that performed the operation that caused the erroneous situation, right? So just to imagine how that works, let's suppose that you were running a program you built and it was a divide by zero error or a memory out of bounds type of error, right? So you try to read beyond the boundary of an array, or you try to read some pointer or reference, but you went beyond its memory segmentation, right? By analogy, any sort of error usually comes up in response to an attempt to run the program that you've written. So that is where the error is seen or read. It's not delivered to some other program that's running simultaneously, but instead to the one that tried to run the offending code, right? So now when this particular thing happens, you see it in that particular context, you're basically going to get a warning that you tried to divide by zero or do some sort of arithmetic error, or that perhaps you have, by means of the currently running program, uh, tried to access, beyond the boundaries of some memory buffer. And it would be addressing that local situation. All right. So that's basically what happens in the operating system. And you can kind of think of it in the similar terms to what you would think of when you get errors when you compile time errors or runtime errors that tell you about your own software that's running. So when signals are generated by events external to a running process, all right, then in that particular case, the process receives the signal asynchronously. So in a an example of an asynchronous signal could include terminating a process with specific keystrokes, right? Like when you've seen me do the Control C or Control Z or using kill, right? Um, or having a timer expire or some asynchronous signal that might be sent to another process, right? These are things that take place without respect to a currently running program in the same exact context, but instead, you have a signal saying, hey, it's time for us to handle such and such event that interacts with the currently running task, but may not have been triggered by the currently running task. So think of it this way. The running process, if I were to pull up my own console and you saw my actual shell or terminal running, and you saw me perhaps having something in that terminal being called, such as my server, which runs perpetually, and then I terminate it using some sort of a hotkey such as Control C, right? That is a an asynchronous event because it's not really the actual when I terminate that web server that ran in the foreground, right? The termination didn't come from within the web server's own execution. It was some event in which I communicated with it, namely using the shell to say, shut this thing down, right? So that's what makes it different from the synchronous ones, in which it would basically be like having an error in that web server, causing the web server to shut down or to enter some sort of error state. So signals being handled. Here's two ways that that happens. You can have a default signal handler or a user-defined signal handler. So think of it this way. It's kind of like when you have errors versus exception handling, right? An error a lot of times in your programs, they're defined in the actual operating system and is implement. I'm sorry, not operating system, but the actual compiler program and their implementations. But you can also say that, if you're checking for exceptions, that certain events that have taken place should not have, and that you're going to then either try to redirect your program or shut it down in a controlled manner, right? That would be a lot like the second case where it's a user-defined handling. So each signal has a default signal handler, and that's run by the kernel of the operating system, the one that is handling that particular signal. So this, however, can be superseded by a user-defined signal handler that is called to handle the signal. And signals are handled in different ways. So some signals, such as changing the size of a window, are simply ignored. Others, such as illegal memory access, are handled by terminating the program. Now, let's suppose that I wanted to actually draw some sort of analogy to all of this. All right. First, let me pause to see if there are any questions thus far. Any questions about signals and signal handling, particularly user-defined and system-defined? Okay, so I'm going to ask my usual question. Who's with me 100% thus far? Not 90%, 100. Okay, one person is. Keep those hands up. Shouldn't just be Ike. Okay, so just one person. All right. I mean, you do remember like how to raise hands here, right? It's either in the more section where you can raise your hand, or it's in option Y, alt Y, that type of thing. But let's see. Any questions whatsoever? All right. So here's what I'm gonna do, just to kind of get us in some sort of way of understanding things. We were talking about, oh, here we go in the chat. Okay, so about the postings, I'm gonna put the lessons up in the YouTube channel after um I have to add to the playlist, but I was gonna, answer that in a little. But I want to hear about questions about user-defined signal handling versus normal signal handling. Okay, who gets this concept completely? Let's just ask that part. Okay, so now here goes. So let's suppose that a signal does come up, right? If we have a signal that comes up for some strange reason, right? Now the question is, where do the signals get delivered? And so now here are a couple of different scenarios. One possibility is that the signal would be delivered to the thread to which the signal applies. Another possibility is that the signal is delivered to every thread in a given process. Another possibility is that the signal would be delivered to certain threads in a process. And then finally, it's possible that you might assign a specific thread to receive all signals for the process. Now, remember that the threads run within the process, right? So we define processes as machine resources and the threads that run within them. So if we have a multi-threaded environment, in that case, there can be various different options for which subcomponents, which threads of execution will be actually hearing about the signals and trying to respond to them. So moving further down, I spoke to you guys about thread pools. That was yesterday. It was somewhat informal, but in a case that we have a thread pool, let's suppose that we have the desire to create multiple in a formal manner, you might say, create multiple threads that will belong to a particular process or a particular batch execution, right? In that case, we can have thread pools, which will create certain number of threads. And in certain cases, also, when certain threads are finished running, more threads can be spawned from the exact same pool, okay? So now, in this particular case, we use thread pool to manage, a large number or significant number of threads that will run concurrently in a given system. All right. And that's what thread pools do. So the idea behind it is to create a number of threads at process startup, place them into a pool where they sit and wait for work. Kind of like that producer consumer thing that showed you the other day, where you have one process that dishes out tasks to the remainder, right? But that's what the thread pool does. It collects these threads together for the surrounding process. Now, when a server receives a request, it awakens a thread from this pool if one is available and then passes the request for service. Once the thread completes its service, it returns to the pool and awaits more work. So it doesn't necessarily just die off because it's finished and terminate, but instead you have, that same pool able to handle more multi-threaded tasks. Okay, so it's not just beginning and then ending after execution finishes. Why we have thread pools is so that we can have certain benefits associated with this, such as being able to service requests with existing threads, right? That's better than trying to create a new thread. It's kind of like when you reallocate memory that was already allocated, knowing that you won't overflow it. And that's easier than trying to see if there is more memory or new memory available. Also, in the case that you have a thread pool, it limits the number of threads that exist at any one point. Usually, thread pools have a size to them, right? So that is a benefit. You can actually know what it is that you're working with. Moving further down, this brings us to another subject altogether. Scheduling. Now, when we talk about the scheduling, I usually refer to this whole thing as job scheduling, but you'll notice that they say the following. However, the terms process scheduling and thread scheduling are often used interchangeably. In this chapter, we use process scheduling when discussing general scheduling concepts and thread scheduling to refer to thread-specific ideas. Okay, so now moving further down, here we are. I have spoken of this before, but now we're finally, speaking of it formally. Here we have CPU I/O burst cycles. Now, first we'll need some sort of definition, right? When we have processes that are to be executed, there is some time spent with CPU resources, such as calculations done in the CPU or anything else that takes up CPU clock cycles. We call this CPU bursts, right? Because remember that we can expect to get interrupted by I/O, and when we have those interrupts, right, the CPU can be its normal mode of execution can be preempted momentarily. So think of it as a burst of work being done, right? So you have process execution. It begins with a CPU burst, and then that is followed by an I/O burst. Remember when we had the interrupt where perhaps I/O asks to do certain things in a process, and it may preempt the CPU's actual execution. This isn't the same as preemption by, say, um, threads or processes that are both using CPU cycles. That would be different. Instead, we're talking about actual control being wrested away from the CPU and the I/O burst coming next, in which process time is consumed by um, actual behaviors or activities carried out by I/O devices. Remember that the actual operating system has to toggle back and forth how to provision resources, and that could even include time to different components, such as the CPU, or a vast array of I/O devices that may also try to use hardware resources or try to be the hardware resources that are used by software programs. So when we have I/O intensive activities, we call that I/O bursts. And this toggling back and forth happens quite a bit. Now, here's the thing, an I/O burst usually takes a bit more time. CPU type of activities are usually quicker and more fast moving, so we can get a lot of work done with the CPU. 5.1.2, CPU scheduling. This part is important. We talked about preemptive and cooperative multitasking, right? And a lot of the things that take place in the execution environment that we speak of in operating systems in this book and in this particular context, we usually talk about preemptive behaviors where um, the CPU doesn't necessarily give up its own control willingly, it's taken away. The only time when CPU may give up control, or I wouldn't even call that giving up control, but may cooperatively move on to other activities is when we're doing job scheduling and the CPU is actually performing CPU activities on different jobs. So whenever the CPU becomes idle, the operating system has to select the process in the ready queue to be executed. Now, remember we spoke about ready queues when we spoke of processes because we said there are different states that a process can have. They can be either, ready or terminated or waiting and so forth. So now you have a short-term scheduler or CPU scheduler which would then pick off some sort of task from that ready queue. And then it tries to assign that task and its associated activities to the CPU. The scheduler selects a process from the process in memory that are ready to execute and allocate the CPU to that process. Now, the ready queue isn't necessarily a first in, first out queue. And that's why this whole CPU scheduling thing is very important and very interesting to learn about. It's not always first in, first out. And conceptually, all the processes in the ready queue are lined up waiting for a chance to run on the CPU. The records in the queues are generally process control blocks of the processes. Remember the process control blocks from the previous chapters? Right. We're going to talk about things in that particular context yet again. So now, preemptive scheduling. In this particular case, the CPU scheduling decisions, they're going to take place under the following circumstances. So number one is that when a process switches from the running state to the waiting state as the result of an IO request or an invocation of wait for the termination of one of the child processes. Okay. Next, another condition that takes place when CPU scheduling occurs. Well, another condition is when a process switches from the running state to the ready state. So this would be like, say, when an interrupt occurs, right? Then after that, the third condition where scheduling could occur is when a process switches from the waiting state to the ready state, such as when we return from completing IO requests. And then when a process terminates, okay? When a process terminates, we move on to another process. So that's not too surprising. So now for situations 1 and 4, there's no choice in terms of scheduling, right? In this case, a process terminated. In the first case, however, a process switched from the running state to the waiting state, which means that that process is no longer running. So the CPU can't actually run on that process that went from running to waiting. So a new process, if one exists in the queue, would then be selected for execution. There is a choice, however, when it comes to these two, with process switching from waiting to ready, and also when a process switches from running to ready. Okay. So when this particular part happens, then we have the following scenario. Scheduling takes place only under circumstances 1 and 4. In those cases, we say that that is non-preemptive or cooperative. All right. The CPU is not getting cut off. It just, has to move on willingly. Otherwise, it's preemptive. The CPU is having control wrested away from it, or, it has to release whatever it is already doing. The process keeps the CPU until it releases the CPU, either by terminating or by switching to the waiting state. This is non-cooperative. All right. So now, moving further on. Remember before we had a dispatcher? Well, we're going to talk about that again. Another component involved with the CPU scheduling function is the dispatcher. And the dispatcher is the module that gives control to the CPU or control of the CPU to the process selected by the short-term scheduler. And this function involves the following. There's going to be some context switching, and we're going to switch to the user mode. And then we're going to jump to the proper locations of the user program to restart that program. All right. Now, remember with context switching, we use that in the case that we were discussing things such as moving between processes and interrupts and so forth, right? Those were just two kinds of context. We had process mode context and interrupt mode context. Here you have a switching to a user mode. Okay. Now the dispatcher should be as fast as possible since it is invoked during every process switch. And the time it takes for the dispatcher to stop one process and start another one is known as dispatch latency. We speak of latency a lot whenever there's a bottleneck within our computer systems. So if there's memory latency, we talk about that as being the downtime between when memory can actually run on the items or the data that's in its memory locations and addresses versus getting more memory or versus not being able to transfer data back and forth between itself and the CPU, right? So latency is any time that we are waiting and not necessarily getting things done. It's basically the hold up time or the bottleneck. So when it comes to scheduling, these are the parts that we're concerned about. I spoke to you about throughput. Here's the official definition. When it comes to throughput, if the CPU is busy executing processes, then work is being done. That's desirable. One measure of work is the number of processes that are completed per time unit, called throughput. For long processes, the rate can be one process per hour. For short transactions, it may be 10 processes per second. Now, CPU utilization. We want to keep the CPU as busy as possible. Conceptually, CPU utilization can range from 0 to 100%. In a real system, it should range from 40%, which is, lightly loaded, to 90%, which is almost used up, but not completely overwhelmed. The turnaround time. The turnaround time is the point of view of a particular process in which an important in which there is an important detail about how long it takes to execute the process in question, right? So it's basically waiting time. Well, no, it's not basically waiting time, but it's the time for executing, right? So the interval from the time of submission of a process to the time of completion is the turnaround time, right? How long does it take for us to put this process in the rearview mirror after we have submitted it for execution? That's our turnaround time. And it's going to be the sum of periods spent waiting to get into memory and waiting in the ready queue, executing on the CPU and doing I/O. That's the turnaround time from waiting to actually get started to actual completion. Now, waiting time is the CPU scheduling algorithm. In the case that it does not affect the amount of time during which a process executes or does I/O, it affects only the amount of time that a process spends waiting in the ready queue. Waiting time is the sum of the periods spent waiting in the ready queue. Now, this may not make sense for the moment, but it will when I talk to you about job scheduling, which is coming up pretty soon. So just keep this part in mind. Now, the response time. Let's suppose that we have a very interactive system. The turnaround time may not be in the best criteria, right? Instead, a process can produce some output fairly early and can continue computing new results while previous results are being output to the user. So another measure that we can use is one of the time from the submission of a request until the first response is produced. And this measure is called response time, right? So now imagine that we have multi-processing going on, and we're not necessarily waiting on another process to finish, but instead we're just waiting for some sort of meaningful progress in the execution of our current process or job, right? That will be the response time, the time that in which we start from the ready queue into actually making some sort of progress, which we get back at least partial results from the process that is running, despite the fact that others are running as well. So this is the time that it takes to start responding, not the time it takes to output the response. And the turnaround time is generally limited by the speed of the output device. All right, so now let's talk about these job scheduling methods. The first one is first come, first serve, right? Now, if you take a look at these particular charts right here, here we have a process, not to be confused with processors, but processes waiting to be run, okay? And then here we have the burst time of how much time they take up on the CPU. And we'll just say that this is going to be theoretical, right? If you want to call it 24 seconds, you can call it 24 seconds. If you want to call it 24 milliseconds, you could do that, but we're using the same exact, um, you might say, unit of time. Here in the book, they're gonna, say it's milliseconds, but if you think that the whole fractional part is hard to work with, don't worry about it. The important part, however, is understanding how these different types of scheduling methodologies differ in things such as allowing there to be, throughput on the CPU and actually being able to finish these processes from beginning to end. So down here, we have something called the Gantt chart, and we have time periods for execution. All right, so process one, they said took 24 seconds up here. So here you go from 0 to 24. And process two, which takes up 3 units of time, it has to wait for 24 to get started, and then it stops at time unit 27. Same thing with process three, in which it starts at 27 and then ends at 30. Now, the average waiting time for a process would be quite large. The waiting time is 0 milliseconds for process one, but 24 for process two and 27 for process three. So the average waiting time is going to be 24 plus 27 over 3, which is 51 over 3, which is 17 milliseconds. If the processes arrived in the order of P2, P3, P1, that would have been much different, right? Then you would have just 3 and 6, right? So then you would have the following. If you take a look here, this is 3, this is 6, and we add those two together. 9 divided by 3 means that we have an average waiting time of 3 milliseconds for those processes. This is what makes it so important. I'm going to pause right here and stop to make sure everybody gets what we're talking about. All right, so pausing. Resume. So now here's what we have. As you can see, we had an average time of 3 seconds if only we took the shorter jobs and put them first. Interestingly enough, there is a such thing as shortest job first. There we go. Shortest job first scheduling. If we can see that certain jobs will be faster to run, then we take the shortest jobs and we run them as having higher priority. This will turn around some of our waiting time. So previously, we had that part about, well, what if we put these shortest jobs up front? What's the waiting time there? Now, let's take a look at this new example, right? So here we're looking at the shortest next CPU burst algorithm. This is a bit more, um, I guess you could say, detailed, right? Accurate in detail. And the reason why we say that is as follows. You may not do the entire process all in one sitting or all in one shot. Kind of like in the real world where you might get up and do something else and have a change of pace and then come back to something you were previously doing. right? So in this case, however, we're going to consider this, as if it's just one, um, one entry and one exit, right? So here we have process 1, 2, 3, and 4. You'll notice that we have burst times of 6, 8, 7, and 3. Well, if it's shortest job first, we're going to go with number 4 first. Then we're going to go with number 1, and then 3, and then 2. So let's take a look. Number 4 came first, number 1, 3, and then 2. So now let's take a look at the average waiting time. In this case, you have 3 for P1, and then you have 9. Let's see, but that would actually, yes, that would be 9 because it's 6 plus 3 for P3, and then 16 for P2. So if I take these three and add them up, I have 3, 9 is 12. 12 plus 16 gives me 28, and dividing that by 4 means I have an average time of seconds or milliseconds of waiting, right? So if we use first come, first serve scheduling, then the average waiting time would have been 10.25 milliseconds. So shortest job first is provably optimal. It's faster because on average they wait less time to get their, most processes will wait less time to start executing and finish. But now, what if we have, say, very, very lengthy jobs and the CPU bursts do not line up with, say, the total amount of time that it takes for us to finish the processes? Well, there's another scheduling algorithm for that one. All right. Moving further down, you would have something called a shortest remaining time first if only we did something called round robin, right? Here's the thing. Before we were talking about first come, first serve, right? Let's suppose that we use some sort of way of dividing this thing up so that we can actually accomplish the beginning of the execution of our processes, regardless of if we can't finish them all in the same amount of time. If we have a preemptive version of shortest job first, then what that means is that the currently executing process can be stopped even if it's not finished, and we can then go on to the shortest remaining job and then do, some work on that one. So let's suppose that we have these processes. There's an arrival time and then there's a burst time, right? The burst time is how much time it takes up. The arrival time is when the process gets there. Notice that for P2, its arrival time is 1 millisecond after the first process gets started or the first process arrives, right? By that time, the burst time for this first process would have been 8 milliseconds. So that's 7 seconds, 7 more seconds than when P2 got there ready to run. 1 second after that came P3, and then another one after that came P4. And here are their different burst times. So now looking at the Gantt chart, we have the following. The processes arrive at the ready queue at the time shown and need the indicated burst times. When the resulting preemptive SJF schedule is depicted in the following Gantt chart, we have this particular layout. All right. So now you see that P2 gets here at time 1. P4 gets here at time 3, but we see that we have a burst time of 5. Okay. So that means it's not going to be finished until 10. P1 gets here at 1, but it takes P2 takes 4 at burst time. We can see that there's preemption occurring here between the different processes. So if the processes arrive at the ready queue at the time shown and meet the indicated burst times, then the resulting preemptive schedule works as follows. So now here is process one. It got cut off by processes 2 and 4, right? So what does that mean right there? Well, process one then had to wait for the remainder of those burst times to finish. So process two, it was faster than process one. So instead, we executed the shortest remaining time, and that was 4 milliseconds. That brings us to the 5 millisecond part, right? So now, by the time we get to where we are at 5, all of these guys have arrived. So now, who's the next shortest after that 4? It's going to be process 4 with 5 burst cycles, or a 5 millisecond burst cycle. So now process 4, since it's the shortest remaining job, is going to run. And all this time, process 1 is being preempted. Process 1 has now waited, let's see, 9 seconds to get back to running. Process 1, since it already spent 1 second running, it's now going to have or require 7 more seconds of burst time. Compare that with process 3, which requires 9 overall. So process 1 is going to go back to running. It's going to take up the remaining 7 seconds and land at 17. And then finally, process 3, which takes up 9 seconds or milliseconds, however you want to look at it. It's going to start running at time 17 and finish at time 26. So process 1 started at time 0. But notice that the average waiting time is going to be a bit different because process 1 now became a process that had to wait. So here's how we do the calculation. You have the process 1 scenario in which there was 0 waiting time here. Process 2 waited 1 second. Okay. Process 4 waited 5 seconds. And then process 1 waited 10 seconds to get back to what it was doing. And finally, process 3 had to wait, let's see, here it's at time 17, but it showed up at time 3. So that was 14 seconds from when it first arrived. All right. So let's just take a look. We have to take away the arrival time from the actual burst times and then average those together. And here we have 6.5 milliseconds. Okay, the average waiting time, if it were non-preemptive, would have been 7.75 milliseconds. So the preemption part actually was more optimal. So now here's something else. I said that, yes, we do use queues, but the way we use the queues is a bit different. This is a priority queue-based algorithm. So with priority scheduling, we don't look at when times arrive, but how important those processes are, reason why they need to finish. So here is the priorities for various processes, 1 through 5. Here's the burst time for them, okay? Even if this one that runs for like 1 second, even if that was very short, the fact of the matter is, if there is a higher priority, the higher priority will run. So let's take a look. P2 has a priority of 1. So P2 runs first, and it runs for 1 second. P5 has the next highest priority, that's of 2. And it's going to run for 5 seconds. Then comes P1 with a high priority of 3, and it's going to run for its entire 10 seconds. Priority P3 has a priority of 4. It runs for 2 seconds. And P4 has a priority of 5, and it runs within 1 second. The average waiting time is 8.2 milliseconds. Okay. The priorities can be either internally defined or externally defined. But how we run these actual tasks, it's going to be based off of some defined priority, not necessarily when we first got there. Nor will it be based off of how long it takes for us to finish. All right. So I'm just going to pause right here and see if anybody has questions. Now, one thing you'll notice, and we didn't get to talking about it yet, is that we're going around in circles and trying to finish these different items in the queue. So in general, here's one scheduling algorithm. It's called round robin. Basically, you make your rounds to all of the different processes. With round robin, imagine that we did first come, first serve, but with something called a time slice. And the time slice is a predetermined amount of time that we'll spend on each process. After we exhaust that, we then go around to the beginning of our queue and then start working on the processes again until all of the different jobs are finished. Okay, so let's take a look at our Gantt chart and our process chart. Here we have P1, P2, and P3. P1 has a birth time of 24. P2 and 3 have a birth time of 3. This was um, our first example. Okay, so now let's take a look here. If we have a time slice, or as they call it alternatively, a time quantum, a quantity of time that is to be allocated. Let's just call it that, all right? Time quantum or time slice, a small unit of time. A time quantum is generally from 10 to 100 milliseconds in length. The ready queue is treated as a circular queue. Once we're done, spending that much time on each of these items, we come back to the beginning and, the ones that are not yet done, we spend more time on them. So here we have the time slice of 4 seconds, and all of these processes are going to be worked on in a round robin way. So process one, remember it's 24 bursts. Its burst time is 24 seconds total. Come in here, 4, but now the remaining 20 are going to wait. We then go to process 2. We finish in 3 seconds. We go to process 3 and finish that in 3 seconds. And then we go back to process 1. All right, so both of processes 2 and 3 have been done because they only took 3 seconds. Process 1, however, still has another 20 seconds that it needs to execute for. So now here you can see we have a time slice that's spent on process 1. It goes from 10 to 14. After that time expires, we then go to look for where to go next, which is coincidentally process 1 from 14 to 18. And then process 1 again from 18 to 22, 22 to 26, and then 26 to 30. After all 30 seconds are used up, 24, 3, and 3, we're done. So that's how round robin works. If some of the other processes were larger, then we would have actually have circled around, not just on process 1, but on the other processes as well. So here with round robin, we have processor sharing, okay? And this is how we execute processes and complete them in that particular methodology. Now there's something called the multi-level queue. All right. So we've got a priority queue. Now we have a multi-level queue. There's a foreground and a background. Okay. And with multi-level queue scheduling, we partition the ready queue into several separate queues, as shown in this figure down here, 5.6. And then the processes are permanently assigned to one queue, generally based on some property of the process, such as memory, size, process priority, process type. And each queue has its own scheduling algorithm. So that means we could be running first job, first search in certain places. We could be running first come, first serve, and so forth. Okay. Everybody with me thus far. Is everybody with me thus far by a show of hands? Let me check the chat. Okay, great. So now moving further on, remember that we have different types of processes, and those processes also have their own priorities. Okay. There's also the possibility of a multi-level feedback queue scheduling algorithm. So this, in contrast to what we've had elsewhere, allows for a process to move between queues. And the idea is to separate processes according to the characteristics of their CPU bursts. Now, this scheduling algorithm leaves I/O bound and interactive processes in the higher priority queues. In addition, a process that waits too long for the lowly priority queue may be moved to a higher priority queue. And this form of aging prevents what we call starvation or the inability to um, get resources. Let me just find you the definition above. Starvation was described above. I'm just looking for it. Let's see. I'll just search for it. Okay, both priority and SJF scheduling may suffer from starvation. Let me just get you the actual definition though. Okay, starvation is also known as indefinite blocking. A process that is ready to be run but waiting for the CPU can be considered blocked. All right, so it is a process that continues to wait. Now, priority scheduling algorithm can leave some low priority processes waiting indefinitely. Let's suppose that another higher priority process shows up despite being having shown up much later than a previous process. That means that the other process won't run. So the one that just can't run indefinitely, that is the one that is starved of resources because it won't enter into the execution stage of its life cycle. Okay, let me just also scroll up one. There's something called aging, and I will discuss that with you. Aging is a technique of gradually increasing the priority of processes that wait in the system for a long time. This would keep starvation from unfolding because the process that waits longer had a um, very great likelihood of increasing its process or priority over time, which means that it's more likely to run than later processes that come in, even the ones that have high priorities. All right, so that's one way to defend against that indefinite blocking. Now, let me just make sure that I can go over this with you right here, multi-level feedback queue scheduling. With multi-level feedback queue scheduling, we allow for a process to move between queues. The idea is to separate processes according to the characteristics of their CPU burst. And if a process uses too much CPU time, it will be moved to a lower priority queue. And this scheme leaves IO bound and interactive processes in higher priority queues. In addition, a process that waits too long in a lower priority queue may be moved to a higher priority queue. Once again, this is aging, right? And it prevents starvation. So that was process scheduling right there. And I would like to get into let me just see if let's see. I would like to get into things like synchronization.